Okay, welcome back. Happy Wednesday. We are getting down to it. Today, class number 32, tailored polynomials is the order of business. Hopefully you're working on project 8. I've gotten some feedback from one person that project 8 can be done pretty quickly if you set your mind to it. So it's supposed to be straightforward. So just be really careful in project 8 that you use complete sentences and that you reference the names of the tests that you use, all the stuff we've been doing for weeks now. Nothing really on the horizon other than turning that project in on Monday. Our third and final test is on whenever this is, May 8th. Is that Friday, a week from Friday? Our third test. Questions on the calendar? Okay. Whose birthday? How did I not? I apologize. Oh, we don't meet on May 5th. That's fine. No. All right. Okay, page 45. Here we go. We'll start with the daily summary. Sam, can you read the daily? 45.
In this section, we meet Mr. Brooks Taylor.
Okay, let's start with number 1 here. Cooper. Okay, so the goal here is to come up with a way to write e to the 2x so that it is approximated by a polynomial. Now think about the graph of e to the 2x. We know that e to the 2x exponential growth, something like that. Yes? Okay, does that look like any polynomial that you know? Eventually, what do all polynomials do when you go far enough to the left or right? They either go up or they go down, right? They certainly don't asymptote at the x-axis. So it does not look polynomial-ish. Furthermore, if you were to compare e to the 2x to, for example, like x squared or x cubed or x to the 5th, which one dominates? E does, right? So even though x squared grows and it goes up forever, e to the x is going to like outpace it very quickly. So even though it goes up forever, it still doesn't look like a polynomial. But the goal is to see if we can try to come up with a polynomial that looks like that, even though that doesn't look like a polynomial. So our first task is to maybe come up with the best degree 1 polynomial that that we can use to approximate our function e to the 2x. So we're going to come up with the best line. Line doesn't look very much like it, but it's a starting place. So what we'll do is begin with this kind of generic way to write a line, a0 plus a1x. It's like mx plus b, but we're going to use a sub some number. And we'll call it p1 because it'll be the polynomial of degree 1. The first thing in the activity will be p2, which will be a quadratic thing. Okay, so a0 and a1 are constants to be determined to try to find the best line that looks like that e to the 2x. And we need to have a starting point. The starting point is it given? Oh, it's not really given. So we're gonna focus our attention on 0, and we're gonna try to make the line look like that curve near x equals 0. So let's first find f of 0 and f prime of 0. So I'm just gonna copy my f function here, e to the 2x. And then I'm going to write my f prime here. So what's the derivative? 2e to the 2x. And now into each of those things, we're going to plug 0. F of 0, f prime of 0. Okay, how much is f of 0? 1, f prime of 0, 2. So far, so good. So that's just the y value and the value of the derivative of the curve, the e to the 2x curve, at x equals 0. Now we're going to come down here and see if we can make it so that P1 matches these two guys. So let's first copy P1. It was A0 plus A1x. A0 and A1 are just constants. X is the variable. Yes, that's going to be the winner. Yeah. Wait, is it? I don't think that's quite the winner, but it's the right idea. Okay, so we're going to try to mimic what we did up here with F, but we're doing it with P now. So let's find P1 prime. Again, A0 and A1 are constants. So what's the derivative of this P1? What happens to that A0 when you take a derivative? That disappears. Derivative of A1 times X is just A1, right? Just like 5X becomes 5. And still mimicking what we did up here, so I'll go to blue now. I'm going to plug what magic number in for these P's? Plug 0 in. 0 is part of the given of this problem. We're focusing our attention on 0 for this whole problem. So plug 0 in for the first guy. What do we get? A0. And for the second guy is A sub 1, right? And our goal is to make it so that the P function matches the F function as closely as possible. So how about we match those two sets of equations right now? Let's make these two guys equal. Yeah, and let's make these two guys equal. So, and those are easier equations than you might normally have, but those are very easy equations to solve. So this tells me that A sub 0 is 1. And the other guy tells me that A sub 1 is 2, yeah? And so that means that our final answer here is P1 of X equals, so all we're doing is copying our original formula, but changing the A0 and the A1 to the numbers that we just found. So A0 plus A1X becomes 1 plus 2X, yeah? And that's it. 1 plus 2x is the best line that we can come up with. It looks as close to that e to the 2x curve as possible, near x equals 0. It only satisfies two conditions. It only has two things in common with that curve. Number one, what do you get when you plug 0 in for x? You get 1. On the curve, what do you get when you plug 0 in for x? You get 1. Okay, so then the line and the curve meet each other at that one point. Super. It's just the tangent line, is all we found, right? We just made it so that the thing we found has the right slope. It has the same slope as that curve, and it doesn't really look like the curve anywhere else except at that one spot, but it's as good as we can do with a line. Okay, so yes, we can differentiate and integrate e to the 2x. But suppose that we gave you something like this, e to the 2x over x, and asked you to integrate that. We actually do have a technique that we could use, but this is not an easy integral, right? It's not just like immediately, oh yeah, sure, no problem. But if instead I could cross off e to the 2x and put a polynomial up there that's pretty close to e to the 2x, like I'll just make something up, x squared minus x plus 2. Let's just say that that's right, but we could do even better with a quadratic thing. But then how could you do this integral? Yeah, couldn't we just split it up into 3 fractions? And then it's all easy, right? So even though, yes, e to the 2x is quite nice by itself, it's not as nice as having a polynomial that we could then split up. There are going to be integrals that we just flat out can't do the way that they are, but we can if we just change something into a polynomial. So, yeah. That's the idea. Yeah, the higher the degree, the closer it is. So that's what you guys will be doing in the activity. I think that's all there is to it. What was it called then? It was called the tangent line. That's all that we found, right? But in the activity, you'll start by finding the quote-unquote tangent parabola, this degree 2 polynomial. So see how far you can get, and I will come around and help out. That's it. Go to it. Well, you got a lot of stuff to do, so go to it.